Hello friends, in the last lecture we have seen some noiseless channel protocols from the subject Foundations of Communication and Computer Network. Today we are going to discuss some noisy channel protocols. So, as we have seen the taxonomy of protocols for noisy channels, three protocols are there. First, stop and wait ARQ, that is automatic repeat request, go back and ARQ, and selective repeat ARQ. Noisy channels. As we have seen, stop and wait protocol gives us an idea about how to add flow control to its predecessor. Actually, noiseless channels are non-existent. So, we are going to consider here noisy channel protocols that are used for error control. So, let's see one by one. First is stop and wait automatic repeat request, that is stop and wait ARQ. It adds a simple error control mechanism to the stop and wait protocol. To detect and correct corrupted frames, we need to add redundancy bits to our frame. When frame arrives at the receiver side, it is checked, and if it is corrupted, it is silently discarded. The detection of the errors in this protocol is nothing but the silence of the receiver. Next, at the same time, it starts the timer. If timer expires and there is no acknowledgement for the same frame, then frame is resent, that is copy of the same frame is held and timer is restarted. Since the protocol uses stop and wait mechanism, there is only one specific frame that needs an acknowledgement, even though several copies of the same frame can be in the network. Error correction in the stop and wait ARQ is done by keeping a copy of sent frame. Here, design of stop and wait ARQ protocol is given. So, at the sender side, data frame contains sequence number, and at the receiver side, acknowledgement from frame contains acknowledgement number. So, sequence number is if sequence number, frame needs to be numbered by using sequence numbers. A field is added to the data frame to hold the sequence number of that frame, and at the receiver side, acknowledgement number is given to the data frame. It is always announced the sequence number of the next frame to be expected by the receiver. For example, if frame 0 has arrived safely and receiver sends an acknowledgement frame with acknowledgement number 1, it means frame 1 is expected next. So here, essence used to refer next frame to send, and RN number refers next frame to receive. At the sender side, three events occur, that is request from the network layer, notification from the physical layer, and event timeout at the data link layer. And one event occur at the receiver side, that is notification from the physical layer. Data frame sent from the sender to receiver, and acknowledgement frame sent from receiver to sender. Next, let's see an example over here. Figure shows an example of stop and wait ARQ. Frame 0 is sent and acknowledged. Frame 1 is lost within the path and resent after the timeout. The resent frame 1 is acknowledged and timer stops. Frame 0 is sent and acknowledged, but acknowledgement is lost. The sender has no idea if the frame data is acknowledgement is lost. So after timeout, it resends frame 0, which is acknowledged. So here, error correction in stop and wait ARQ is done by keeping a copy of sent frame and retransmitting of the frame when timer expires. In stop and wait ARQ, we use sequence numbers to the frames, and sequence numbers are based on modular truth arithmetic, that is, XOR operation can be performed as a sequence number. In ARQ, we can find a solution in this way, such as give a number to the frame such as sequence number. When receiver receives a data frame that is out of order, this means that frames were lost or duplicated. The corrupted or lost frames need to be resent in this protocol. If the receiver does not respond, then there is an error. Here we have one problem, that how can senders know which frame is to resend. To solve this problem, sender keeps a copy of send frame. At the same time, it starts the timer. The timer expires and there is no acknowledgement for the sent frame. Then frame is resent and the copy is held, and then timer is restarted. Next, another protocol we can see here, go back and automatic repeat request. To improve the efficiency of the transmission in the pipe, that is in the transmission path, multiple frames must be sent in the transition while waiting for the acknowledgement. One frame be outstanding to keep the channel busy while the sender is waiting for the acknowledgement. That means in go back N, multiple frames can be sent at a time and wait for the acknowledgement. Here we can send several frames before receiving the acknowledgement. We keep a copy of these frames until the acknowledgement arrives. In go back and automatic repeat request, we use sequence numbers also. Frames from a sending station are numbered sequentially. If the header of the frame allows m bits for the sequence number, then sequence numbers range from 0 to 2 raised to m minus 1. For example, if m is 4, we consider here example number of bits as 4. The only sequence numbers are 0 to 15 inclusive, that is inclusive 0 to inclusive 15. However, we can repeat the same sequence, so the sequence numbers are 0 to 15, and then in the next cycle again 0 to 15. In other words, the sequence numbers are modulo, that is 2 raised to m. The same thing is noted here, where m is the size of the sequence number bits in bits. Next, we use the concept of sliding window in the protocol. The range of sequence numbers, that is concern of the sender as well as the receiver. The sender and receiver need to deal with only part of the possible sequence numbers. The range, which is the concern of the sender, is called send sliding window, and which is concerned to the receiver is called receiving sliding window. Here, the maximum size of the window is 2 raised to m minus 1. The first region from the left to the right, that is the left wall of the window, defines the sequence numbers belonging to the frames that are already acknowledged. The second region defines the range of sequence numbers belonging to the frames that are sent and have an unknown status, that is, they are not acknowledged yet. The sender needs to wait to find out if these frames have been received, or lost. We call these as outstanding frame. The third range, that is shown in white color in the figure, defines the range of sequence numbers that can be sent but not yet received from the upper layer. the corresponding data packets have not been received from the network layer. And finally, the fourth region defines the sequence numbers that cannot be used until the Windows slides. So here sliding window size is total 15, where number of bits are 4. Therefore, we can use formula 2 raised to 4 minus 1 is equal to 50. At the receiver side, then send window after sliding first outstanding frame, then SF denotes send window first outstanding frame after sliding, and SN denotes the send window next frame to send after sliding. Send window is an abstract concept which defines the imaginary box of size 2 raised to m minus n, where three variables we can use here: total size of the window, that is 2 raised to m minus 1, SF and SN. The send window can slide one or more slots when a valid acknowledgement receives. The receive window is an abstract concept of defining imaginary box of size 1 with one single variable r n. Window slides when a correct frame has arrived and sliding occurs one slot at a time. That is shown in this diagram. Receive window for go back in ARQ. Receive window as well as window after sliding. Acknowledgement. The receiver sends a positive acknowledgement if frame has arrived safe and sound and in order. But if a frame is damaged or received out of order, the receiver is silent and will discard all the subsequent frames until it receives the one it is expecting. The silence of the receiver causes the timer of the acknowledged frame at the sender side to expire. This causes the sender to go back and resend all frames beginning with the one with the expired timer. The receiver does not have acknowledged each frame received. It can send one cumulative acknowledgement for several frames. Next is resending a frame. When timer expires, the sender resends all outstanding frames. For example, suppose the sender has already sent frame 6, but the timer for frame 3 expires. This means that frame 3 has not been acknowledged. The sender goes back and sends all frames, that is 3, 4, 5 and 6 again. That is why this protocol is known as go back in ARQ. So in the design of go back in, same thing is represented here. First outstanding frame is denoted by SF. Next frame to send is denoted by SN. Data frame is having sequence number and acknowledgement frame is having acknowledgement number. In the pipeline of the transmission path, number of frames sent at a time. So 3 events occur at the sender side and 1 event occur at the receiver side. That is request from the network layer, notification from the physical layer as well as timeout event. And notification from the physical layer is occur at the receiver side. Next is send window side. We can have now shows the size of the window, that is send window must be less than 2 raised to n, that is 3. So here we can choose n is equal to 2, which means that size of the window can be 2 raised to n minus 1, that is equal to 3. If the size of the window is 3, that is less than 2 raised to 4, then all 3 acknowledgements are lost. The frame 0 timer expires and all 3 frames are resent. The receiver is now expecting frame 3, not frame 0. So duplicate frame is correctly discarded. If the window size is 2 raised to n, that is, if the size of the window is 4, that is equal to 2 raised to 2, and all acknowledgements are lost, the sender will send a duplicate frame of frame 0, and this time the window of the receiver expects to receive frame 0. So it accepts all frames not as a duplicate but as the frame in the next cycle, and it is an error. The same thing is shown in the diagram. In the first figure, sender and receiver having window size 2 raised to m minus 1, that is less than 2 raised to m. When we consider here m is equal to 2, then size of the window is 3. If size of the window is 3, then if all 3 acknowledgements are lost within the path, then frame 0, frame 1 and frame 2 are passed from sender to receiver. The timer 0 expires and all 3 frames are resent. The receiver is now expecting frame 3, not frame 0. So, duplicate frame is correctly discarded. Sorry. In another diagram, if the size of the window is shown here 4, that is equal to 2 raised to 2, and all acknowledgements are lost, the sender will send a duplicate of frame 0. However, this time the window of the receiver expects to receive frame 0, so it accepts the frame 0 not as a duplicate but as the first frame. This is the first frame in the next cycle. Therefore, this is an error, and erroneously this frame is accepted. So here one note is given. In go back in ARQ, the size of the send window must be less than 2 raised to m. The size of the receiver window is always 1. Here one example is given. This is an example of a case where forward channel is reliable but the reverse is not true. No data frames are lost but some acknowledgements are delayed and one is lost. The example shows how cumulative acknowledgements can help if acknowledgements are delayed or lost. After initialization, there are 7 sender events. Request events are triggered by data from the network layer. Arrival events are triggered by acknowledgements from the physical layer. There is no timeout event here because all our outstanding frames are acknowledged before the timer expires. Note that although acknowledgement 2 is lost, acknowledgement 3 serves as both acknowledgement 2 and acknowledgement 3. Advantages. The benefits of go back in ARQ. It simplifies the process at receiver side. Receiver keeps a track of only one variable. There is no need to buffer out of order frames. They are simply discarded. Some drawbacks are mentioned over here. Go back and ARQ is very inefficient for noisy viewing. In a noisy viewing, a frame has higher probability of damage, which means resending of multiple frames. This resending uses up the bandwidth and slows down the transmission. Next is selective repeat ARQ. For noisy viewing, there is another mechanism that does not resend n frames when just one frame is damaged. Only the damaged frame is resent. So this mechanism is called selective repeat request. So damaged frame is only selectively send or resend from sender to receiver. Selective repeat send window. The send window maximum size can be 2 raised to n minus 1. For example, n is equal to 4. Sequence number goes from 0 to 15. but the size of the window is just 8 because we have n is equal to 4. Therefore, formula becomes 2 raised to 4 minus 1 is equal to 8. It is 15 in the go back n protocol. The smaller window size means less efficiency in the filling of the pipeline. The protocol uses the same variable as we discussed for go back n. In this diagram, same window for selective repeat ARQ is shown. So same window is having maximum size 2 raised to n minus 1 where n is equal to 4. Sequence numbers go from 0 to 50. First region is shown, that is frames already sent and acknowledged. Second region, frames sent but not yet acknowledged. Third region, frames that can be sent, and fourth one is frames that cannot be sent. And size of the window is 2 raised to m minus 1. So here size of the window we can taken here just as 8, not 50. Next, receive window for the selective repeat request, which is shown here. Receive window is having Rn, receive window next frame to be expected. First region shows frames already received. Second region, frames that can be received and stored for later delivery. The colored boxes shows the already received frames. And last region, nothing but frames cannot be received. Stop and wait ARQ is a special case of go back n ARQ in which size of the send window is 1. The design of selective repeat request. SF denotes first outstanding, SN denotes next frame to send. Data frame is having sequence number as well as acknowledgement, and not acknowledgement frame is having acknowledgement number or not acknowledgement number. 3 events occur at the sender side as well as 1 event occur at the receiver side. Then next point, window size. We can show the size of sender and receiver windows must be at most 1/2 of the 2m. Where we choose here n is equal to 2, then size of the window is 2 raised to m minus divided by 2, or compare the window size of 2 with a window size of 3. So in this diagram you can see selective repeat ARQ window size. Here we can choose n is equal to 2. So first window identified as window size 2 raised to m divided by 2 or 2. When it compares window size of 2 with window size of 3 as shown in the next column, if the size of the window is 2 and all acknowledgements are lost, the timer for frame 0 expires and frame 0 is resent. However, the window of the receiver is now expecting frame 2, not frame 0. So this duplicate frame is correctly discarded. When the size of the window is 3 and all acknowledgements are lost, the sender sends a duplicate of frame 0. This time the window of the receiver expects the received frame to receive frame 0. That is 0 is a part of the window. So it accepts frame 0 not as a duplicate frame but as the first frame in the next cycle. So this is clearly an error and which is accepted at the receiver end. In selective repeat ARQ, the size of the sender as well as receiver window must be at most 1/2 of the 2 raised to m. Here in this diagram, flow diagram is shown for selective repeat ARQ. So each frame sent or resent needs a timer, which means that the timers need to be numbered 0, 1, 2 and 3. The timer for frame 0 starts at the first request but stops when the acknowledgement for this frame arrives. The timer for frame 1 starts at the second request, restarts when not acknowledgement arrives, and finally stops when the last acknowledgement arrives. The other two timers start when corresponding frames are sent and stop at the last arrival event. At the receiver side, we need to distinguish between the acceptance of a frame and its delivery to the network layer. At the second arrival, frame 2 arrives and is stored and marked, but it cannot be delivered because frame 1 is missing. At the next arrival, frame 3 arrives and is marked and stored, but still none of the frames can be delivered. Only at the last arrival, when finally a copy of frame 1 arrives, frames 1, 2 and 3 be delivered to the network layer. There are two conditions for the delivery of the frames to the network layer. First, a set of consecutive frames must have arrived, and second one is the set starts from beginning of the window. Not acknowledgement is sent after the second arrival, but not after the third, although both situations would be the same. The reason is that a protocol does not want to crowd the network with unnecessary not acknowledgements and unnecessary resent frames. The second not acknowledgement would still be not acknowledgement 1 to inform the sender to resend frame 1 again. This has already been done. The first not acknowledgement sent is remembered, that is not acknowledgement sent variable, keep this value, and is not sent again until the frame slides. A not acknowledgement is sent once for each window position and defines the first slot in the window. Here, only two acknowledgements are sent. The first one acknowledges only the first frame and second one acknowledges 3 frames. The selective repeat acknowledgements are sent when data are delivered to the network layer. If data belonging to n frames that are delivered in one shot, only the one acknowledgement is sent for all of them. Limitations of selective repeat request. ARQ. All are unidirectional. Data frames flow in one direction and control information such as acknowledgement and not acknowledgement frames can travel in other direction. Next is piggybacking. In real life, data frames are normally flowing in both directions, from node A to B and as well as from node B to A. This means that control information also needs to flow in both directions. This technique is called piggybacking, which is used to improve the efficiency of bidirectional protocols. When frame is carrying data from A to B, it also carry control information about arrived or lost frames from B. When frame is carried from B to A, it also carry control information, that is acknowledgement and not acknowledgement about the arrival or lost from frame A. In the diagram, send window, receive window as well as send window and receive window are maintained at the sender side as well as at the receiver side. Frame is having acknowledgement number as well as sequence number. Frames are flows from sender to receiver as well as from receiver to sender with acknowledgement number as well as sequence number. Events occur at the sender side as well as the receiver side are same, that is request from network layer, notification from physical layer, as well as event timer. In this way, we have seen some noisy channels protocols. Okay, thank you.